Okay. Welcome to everybody. I think you can hear me. I can hear you. Some of you at least, if he's not muted. Yes. Welcome everybody. I can read the chat. Yeah, perfect. So let me start this lecture and share the screen. And I once again, I won't have like the full control over the chat, okay? Because when it is in full screen mode, it's rather difficult to get it as.
Professor.
Yeah.
I'm sorry. Can you start recording the lecture, please?
Yes. I will start in a second, Aurelio.
Thank you.
But first, I want to ask whether there was some question on your side since the last lecture of yesterday, something which is not clear. Because some I will touch again some aspects. I will start from a short recap of the last part. But if there are some questions, please just unmute yourself and ask. Then I will start recording. I will start the lecture. So everything was very clear to all of you. Yes. No questions. Okay, then let's start. And Fabio has one question. Wait. I would like to ask if the linear transformation simply apply correlation. Yes. This is what I'm going to recap now. So, Fabio, let me know if after this short recap I'm giving now, everything will be more clear or what. I know because yesterday in some cases I had to hurry up a bit at the end of the lecture, in particular of the second recording, so it might be, difficult to grasp. Some of you might have like missed something. Okay. Okay. So for any other question, just feel free to ask. Just interrupting me when needed. So today we are getting into the right way of classifying images. Okay. Wait, there is one other question. The first time we talk about correlation, the result was an image, while at the end, when we build the network, the result was a scalar. Are the same correlation? Yes, Enrico. Yes. And the point is that when you do a correlation, an image against a filter, what you get, it's a scalar. And then you repeat the same by changing the reference pixel, which means you move the filter to the image. But since now the two images have the same size, you're not moving them. So it's like computing the correlation at the center of the image. Okay? Thanks. So, yeah, Carlo, how can I, but please unmute yourself. It's going to be easier, more interactive for me rather than reading the chat. How can I do correlation in the borders of the big image? There are padding options, which is something we are going to see today. There is a slide on that. Okay, now I've closed the chat. Just ask if needed. Now, so to recap the experiment we have seen yesterday. Okay, we are given an image, we unroll it, unfold, whatever we want to call it, to place it in a vector, because given a vector, we can apply any classifier we are used to. I mean, you have seen neural network in this course, but I'm sure you have seen maybe others if you have been attending if you are attending machine learning. So And what I told you, I'm going to take the simplest ever classifier, which is the linear classifier, which means that my score, my output is going to be W times X plus B. Now, X, as you remember, is the image, but placed in a vectorial form. And then we train, and this is equivalent to train a network, which is, so this is n-dimensional vector, where n is the number of pixels, right? So 3K for cipher images. It's equivalent than training a network which has fully connected, feed-forward neural network, which has n neurons in the input layer and 3 neurons in the output layer, no hidden layers. And these weights, so the weights connecting all the input neurons to the first output neuron are actually these, well, it's not all these weights are actually what you get in that matrix, right? In the first row of that matrix. And now what we were saying is that, look, if we take this matrix once trained, or take the network once trained, and each row corresponds to the weights associated to each output neuron, of course, then we can unfold this row vector and reassemble an image. And this is meant to really have an interpretation of what's going on, of what this classifier does, how the image is being handled, right? And what we get is these kind of images, which I taken from this website, and I received some comments yesterday after the lecture, and I received even emails from some of you. Thanks a lot for your feedback. I mean, here I was a bit cheating because the weights, even as I wrote here, might be negative, might be, of course, non-integer, might be over the image range. So there is some kind of normalization in order to get these images, which I took these images as a result from an experiment described in that website, in that, it's a Stanford course on computer vision. So it's not, I didn't take care of the normalization myself, okay? So, but that's an issue, of course. You need to do some kind of rescaling of these in order to get these nice images in between 0 and 255. And so these images are the result also of that normalization. But I think that except from the normalization that you do, you would get very similar images to this. And the idea now of the interpretation, I've prepared this additional slide, is that in order to classify an input image, so this is I, input image, when you want to classify this input image, what you do is, in principle, to compute the inner product between each row of the matrix and each column, in the column of the image, sum the weight, sum the bias, and get the score. And this can be also interpreted as performing a correlation between the two images. And so the correlation was something, this is the formula I wrote last time. Now the formula would be T, right, of, this is the template, okay, say T1, template for the first class, which is nothing but the row, the weights of the neural network, times R E times E, R plus X, C plus Y, what you see here. And what you expect is that this product is larger when the template corresponds to the class where the image belongs to. And now there is this issue that, I mean, these are the same size. So as I told you before, it's like if you're computing the correlation with respect to the pixel that is at the center of the image. So it's the correlation in a single point. So you can imagine that R and C are kind of disappear, and you consider X and Y to span to the whole image coordinates. And you sum them up. Still, it's like you overlap the image, you overlap the template, compute the element-wise product, sum all the results. But now, the problem is that I told you how to compute the correlation between an image, which was grayscale. Here I'm telling you, you have to do the correlation between these images, which are color images. So they have 3 planes. So this is the image, this is the template, say T1, whatever. So you have 3 color planes. How to perform correlation? This is performed like layer-wise. So the first layer, the red channel of the image, correlation with the red channel of the template, okay? And what you get out of this is going to be a number, because this is more, this I prepared in advance, so it's there, I cannot remove it. It's Ri correlation RT, where RT is the red channel of the template, Ri of the image, like assessed in 0, 0, like in the center of the image or whatever. Plus you sum the green channel, the correlation with the green channel of the other image. You are not, of course, you are not. This is what I want to make clear in these experiments, but also in convolutional neural network. You are not mixing in this correlation different channels, in a sense that you are not using the red as a weight for the blue. Okay, there is a channel-wise correspondences. So you only compute this element-wise product between corresponding channels. Okay, and so because you might think of, if this is the image and you were moving in this direction in order to compute the correlation against a filter, you might wonder whether you have to move also along this direction, the channel direction, but this is not the case. Okay, so the correlation among these, formulated like this, it is exactly as computing W1, say the first weight corresponding to the template 1, the first row of the weighting matrix, times your input image X, say the vector X corresponding to the image. And now if you look at these, so the template being blue means that on the blue channel you have large weights here. And maybe you have very low weights or even negative weights in principle over the red and the green channel. Okay? So this means that here in the product you will get large numbers if there is a lot of blue here, okay, in those pixels, and then this will contribute to get a large weight at the end of the day. Instead, if you take, say, some different background, so like in this case, when you want to compare against the car and assume that this background is kind of red, say it's not blue, what you get in the red, over the red channel, is that the weight here say there is mainly the red channel and the blue is going to be almost 0. So you see that here there is only blue. So the final score contributing of all these regions will be approximately 0, because say, there is no blue in the weights when you do the element-wise product. Okay? Is there? I see plenty of comments in the chat. Do something you want to say? Okay, so I have to fix the slides. Is there some comment I shouldn't add? Okay, now it's too late. You got it. Was it something very terrible?
No, I think someone just went on the last year's site instead of this year's and couldn't find the slides for this lecture.
Okay, so yeah. Okay, thanks. Let me just check it out for a while. What's going on? Okay, I'm back. I will check later. It's gonna be take longer. Okay, so now, so you see now what the classifier can learn. Basically, it will learn, say, some very large, say, major feature in the image, and like the background or like the background color or whatever. But it won't detect what are the most relevant patterns inside the image. However, I'm telling you this example because this is a mechanism, say the fact that you compute correlation between the image and some pattern, some template, then this is very, very useful to understand, because this is what the convolutional neural network will do at the very beginning. So by designing a different architecture where we see the convolutional neural network and designing them for, say, to make it, by stacking multiple, we see multiple layers of this kind of operation, this correlation, the neural net, we will design neural networks that are able to highlight small or increasingly large pattern inside the image that can make clear distinction between what the objects are. So not only macroscopic features, say, from the background, but rather most important patterns that are discriminative for the object content. Okay? So is there any other comment or question? Okay, there was a problem with the link. So the weights, so was it clear, Simone, now the weights, where are they from? They are, you estimate them by training the neural network or training the linear classifier, okay? After training, you got the weights. Now, the right way of handling images, so it's certainly not using just a linear classifier directly from the input, and the approach that was like mainly pushed in the literature was to perform feature extraction. So what you would like to do is like to make a pipeline of algorithms. So the first one, the input image, which has like a varying size, whatever, it's being processed by an algorithm which we call feature extraction, which is something that it's manually designed, for example, that used to be like manually designed by an expert, which provides you a vector of meaningful information for determining the class of the image, the class the image belongs to. So, for example, I'm giving you an illustration right now, but you have to think like this feature extraction algorithm, like a way to move out of the image world, which is rather difficult to handle because of all these challenges I was mentioning before, let's say in the last lecture, and because of this very huge dimensionality, to move into a standard setup where inputs are represented as vectors, and the dimension of the input is much smaller than the number of pixels in the image. And then you perform classification over this extracted feature. And this classifier can be your favorite classifier, maybe a neural network, or even maybe there does make sense even a KNN or whatever simple classifier. So when you feed another image to your feature extraction algorithm, you will get a different feature vector, and the classifier will provide hopefully a different output. And this is like, as I was mentioning before, this feature extraction algorithm, this part, this used to be, and still in some cases can be, expert driven, which means that there is some engineer, some doctor, some scientist, whatever, that is taking care of providing good features to be extracted out of the images that are meaningful to solve the classification problem. So, for example, just to give you an idea of what is expert-driven feature. So, if you want to implement an algorithm that classifies like heartbeats, so this is a scheme of the shape of our heartbeat from our ECG tracings. Then, if you analyze doctors, when doctors analyze these shapes, they maybe measure or somehow assess certain specific patterns and certain measure, certain distances, like the size of this peak or other intervals inside this signal, and then they perform a classification whether the heartbeat is healthy or there is some issue or some kind of arrhythmia or whatever. So an expert-driven feature, what you can do, what can be an expert-driven feature in this case would be to design algorithms that select these points or these points and measure these distances in an input sequence. Okay? And then your feature vector will be like this, like 5, right? 1, 2, 3, 4, 5, and each of these will be stacked in a vector, in a location of the vector. And then you can train a classifier that indeed classifies the signal, but in reality, the information that can be included in the signal has been already extracted. See, all the information you can use has been already extracted by the engineer or the doctor who has designed this algorithm for selecting these regions. Now, how to do feature extraction in images? So how to extract handcrafted features? So images that are acquired from, I'll give you an example of a project we have been addressing a few years ago. There was this company coming to us that wanted to perform classification of the parcels that were like moving over a post or over a tray in a post office to be dispatched. And the first problem was to classify these parcels in 3 categories: envelope, parcel, and double. So this is an envelope, it's a very tiny image because it was acquired by an RGBD sensor. So these images are like depth images. So these are not color images itself, but they are just measuring the distance or the height from the ground of the parcel. Okay. Now this is the envelope. It's like a bag, and there were double, which was the most interesting class because there were 2 objects too nearby, too close. The machine had to somehow move them in order to separate them to be better than dispatch them and processed by the tray that was moving these parcels, and then there was the parcel which was like a box containing a book. Okay, so what they wanted to do was a system able to classify these images, which were rather small, as you can see, and were scalar images, say, okay, grayscale images, because their information was just the depth, it was not correct. And of course, now if you take a good engineer, you will give these images, and he will start thinking some good criteria to separate these into the three categories requested. And for example, he would believe that, for example, the area, right? So the area of the parcel would be meaningful for separating them. And I mean, this is very reasonable, because I mean, if there are two, you would expect the area to be larger than if there is just one. But similarly, you can also look at the variance of the height that you measure over the parcel. So here the parcel is flat, so you won't have much variation in the parcel. Or you might look at the shape, at the perimeter, or whatever. Histograms you can compute of the heights, and taking some quantile or some values out of the histograms. So what you do is that you associate to each of these image a kind of vector. I've missed the slide. Sorry, I've missed the slide with the vector. Here's some problem with the slides, apparently. And in practice, you might compute all these quantities, but let's just stick to a simple case where out of your image, you compute only two measures. The average heights, so two features, and the area. And then you feed these, you can feed these to a classifier or to a neural network in order to recognize what would be, say, here is a classifier. And there is the feature extraction. Then the classifier will figure out what are the three classes: parcel, double, or envelope. So this is, I mean, great, because you are given a training set. Now, out of the training set of images, which are here denoted, where the label is denoted by the color, like the red, green, and blue, what you get is that each image corresponds to a point in a two-dimensional space. It's two-dimensional because we took only two features: the average height and the area. Okay, and the training set actually would be represented also in a plane, where you have like these measures with these feature vectors that are spread through all the plane with different markers and different colors indicating different classes where the image belongs to. And now this is now these are a short excursus. What the guys were doing, we're actually manually designing some rule in order to identify when the image belonged to one class or the other, right? So only two features. Okay, not only, they were using plenty of features, but here we have only two features. And so, I mean, by looking at the training set, you can manually set this kind of threshold. They say that if the height is below 2.5, then you can consider the label to be a parcel, like the red is parcel. And then if the height is larger than 6.2, which is this point, then it's an envelope. And then here in between, you might cut it further. So if you are in between these two values of the height, the average height, you look at the area. If the area is above 200, then it's going to be a double, otherwise it's going to be an envelope. Of course, these are trivial examples. And by using this classifier, what you get is that you got different, you have divided your input image, you have divided your plane where your input image will fall thanks to the feature extraction into different regions, in this case 4 regions, and you have been associating to each region a label, right? Can you tell, okay, to which classifier this image these would correspond to. I mean, it's already in the slide, so I've already mentioned this. We have already shown this a bit. This corresponds to a tree, to a classification tree, right? Exactly, already. And this classifier, it's manually designed. Can be manually designed or can be at the same time trained by minimizing some loss over the training set. And you can see that the splitting criteria are rather simple, right, over each leaf. And of course, there are some drawbacks here because that was the actual feature distribution for a pair of features. And indeed, you can see that, I mean, by manually selecting some vertical or horizontal crop, it doesn't work, but it would be better to design like diagonal cuts. And this would mean that the rule for the splitting rule over the tree should be a linear function, like in this case, instead of a simple comparison against a threshold. And of course, okay, here I can jump to the next. Of course, this prevents you to design the classifier yourself, and rather you should resort to some data-driven model, like training by minimizing some loss, and still the classifier you have chosen there cannot provide a nice separability among the regions of the feature. So it would be better to say take a more general model, like in this case a neural network that might take, say, decision boundaries between the classes which are say not parallel to the axis. So what the simplest thing you can do to combine what would be like the experience of the expert, of the engineers, to address that problem is to ask them to extract features for you, and then resort to a data-driven model, a classifier, for separating the images into different regions. And this is exactly what we can do by feeding this feature extracted from the image to a neural network. Okay? And so the input layer will have the same size as the number of features. The output layer, the number of will correspond to the number of categories, and each value in this will correspond to the probability of the sample to belong to the given class. And you can take an arbitrary large number of hidden layers. I don't need to tell how a neural network is to you. So that was just to give you the general picture that in many cases, in some cases, and in all the cases like 10 years ago or 8 years ago, the image classification problems were solved by combining two different models. The first one, two different, say, algorithms. The first one was a feature extraction algorithm that was entirely handcrafted, while the second one was a classifier, support vector machine, or a neural network or whatever, that is entirely data-driven. Because experts can be good at implementing feature, but then it might be, of course, difficult to implement the classifier to separate. And once you're here, once you get to you get to a vector, you are in the customary settings for training a classifier and using it. So it's okay to have it was very successful to combine the two. The problem is that, so on the one hand, the advantages of this approach is that you can already get what is very meaningful out of the images in order to define the classes. You don't have to analyze like the values of the raw pixels directly and hope the network somehow to provide you the interpretation. Then you can also adjust features to improve. You can improve, say you discover something new for solving this classification problem, you can bring these into new features that can further improve the classification performance. You get some interpretability. You don't have interpretability in the decision, except if you don't take a very simple classifier, but still, you know what your classifier is looking at. And oftentimes, this approach is viable when you are given a limited amount of training. Because the tough part of the job, which is to extract the meaningful feature vector, here is feature vector, is being solved by an expert. And it's directly encodes information from him, from his own experience. Of course, I mean, if you are a lazy programmer, this is not a nice approach to push you. And most importantly, it is not viable to solve many visual recognition tasks. Say if you take even the picture of a wheel, which is very simple to recognize to our understanding, well, it won't be the same easy to identify some feature that is telling you how many steel lines, steel bars going to the center of the wheel are there in an image. Like, because if you believe that this is a peculiar structure of an image, right? Of a peculiar feature, so the number of these steel bars is certainly meaningful for determining whether an image is contains a wheel or not, but it's not going to be easy to design an algorithm that is giving you a feature that is telling you how many of these bars are in a wheel. And then it's also very difficult to port them, because if you have trained a classifier for the wheel, then you are asked to solve it for the class of cars. Already you have to redesign everything completely. And there is a risk of overfitting, because typically when you start implementing, when the training set is small, and you design your technique by yourself, you can introduce a kind of the feature extraction can also suffer from overfitting, in a sense that you might consider only a partial view over the characteristic defining the image to belong to a given class. And so a more appealing perspective is to resort to a data-driven model, and in particular, we will see a neural network also for the feature extraction part. And this is going to be great. And so this is very appealing because as the feature extraction, as for the classification, it would be difficult to define rules ourselves. You would expect like the same from defining the feature extraction part. And so if we can improve the classification performance by resorting to a data-driven model, maybe we can improve also the feature extraction by resorting to a data-driven model. Most remarkably, but if we resort to a data-driven model, we can train these two jointly, this model and this model jointly, to optimize to minimize, for example, the classification error, which would imply that the feature extraction part will be also optimized to solve the classification, to minimize the classification. So here are the big breakthrough in 2012 was to make some convolutional neural network to work. And this convolutional neural network, which were like actually have been proposed way before, say in 1997, the convolutional neural network is a network that can be used for this task. And we will see this today. So let me set up the stage, and then we will go to the convolutional neural network. Is there any question, any comment, anything from the chat? No, just answers. Everything is clear? Please give me a feedback or just unmute yourself if you have any question. Yes, everything okay. Good. Okay, so let me set up the stage. So convolutions, I'm providing you a different illustration of what a convolution is, but because this is maybe is more fancy. But as you can see here, that was the formula you have seen yesterday of the correlation, where we have a weight matrix, the filter, let's call it filter. This is being overlapped to each pixel on the image. You compute the element-wise product, as you see here in this three-dimensional fancy illustration. You see you are computing the element-wise product between the image and the filter, and what you get as output is a single number to be placed in the center. Right? And the operation is exactly this. So this is correlation. Convolution is just this guy. So what actually changes is just a minus sign here. And historically, convolution was defined with the minus because then it is because then in the Fourier domain, the convolution corresponds to a product, an element-wise product. A convolution in the space domain becomes a product in the Fourier domain. So for these nice properties in harmonic analysis, in the Fourier transform. But still, nothing changes. If you consider that your filter, which is here defined as W, it's simply flipped. So you flip your filter vertically and horizontally, and then you use it as if you are doing correlation, right? So you talk about convolution, but indeed it's the same mechanism of correlation up to flipping, the filter. Now, this is entirely irrelevant to us now, this flip, because what we will do is to use weights, say instead of using weights that are defined a priori, as you do typically in signal processing or in image processing where the filter is somehow given or designed, here we will learn the filter coefficients. So it's not relevant at all if you have to place here a plus or a minus, because this would imply that just to flip the filter coefficients. But indeed, since the filter's coefficients will be learned, then, I mean, you can use a correlation and you will learn the filters that are flipped with respect to what you will get if you are learning the convolution. So I think this is entirely irrelevant to us, and whether there is a minus or a plus there, since it will just imply to flip the filters, and the filters will be learned. Okay? So there was a question at the very beginning, and the question was how to perform convolution where the image or correlation, whatever, when the image at the image borders say how to compute the output here, considering that the input image is just the blue or the violet region. So you want the output to be defined. If you want the output to be defined also here, when you superimpose the filter in order to compute the element-wise product, you need to define some value out of the image to be superimposed to this portion of the filter that wouldn't be otherwise considered. And there are different options. The most, frequently encountered, I would say, is to perform padding, which means that you add enough rows and columns of zeros such that the output of your image has the same size of the output image has the same size of the input. this would somehow imply that the value here is getting darker because we have plenty of zeros here, and okay, then it depends on the coefficients of the filters. But say if all the filters have positive coefficients, then this would result in a darkened board boundaries. That's true. You can see this. If you open like Python, you do convolution, two-dimensional convolution, and you set the padding option. In MATLAB is conv to EF, the filter, and then you type same. In order to provide the same output, the same size the output as the input, the default option is to pad with 0, which means to have darkened both top and bottom rows and left and rightmost columns. And the larger the filter, of course, the darker the borders are. But this is not the only way of performing convolution. This is like the padding option, where you include some elements outside. Actually, the padding with 0, so where you place 0 here, is the most frequently encountered in these cases. But when you were doing like operations in Fourier domain, you need to have periodic signals. So here you were putting you were padding the signal to be periodic. So you were taking the values on the other side, right? Or you were also mirroring. In some cases, you were mirroring the values. But most often, for us, it will be pad with 0. And this will preserve the size of the output. So this is the input. This is the output. And you can see the filter moving and highlighted in the output the pixel where you set the value of the output. There are also other options where the output is computed only in locations where the filter is entirely included in the image, right? So in this case, you start from an image which is 4 by 4. You are performing convolution with a filter that is 3 by 3, and only for these 3 central pixels, you can place the filter there, and compute the output, right? So the output is 2 by 2. Otherwise, there is also the full padding, but you never do this in convolutional neural networks, because these would increase the size of the image, and this is obtained by padding the image of a size that is typically larger than what you pad from to guarantee the same. And you define the output even in those pixels, like this one and this one, that are like outside of the image region. And still, some value can be defined here and here as well, because the filter still overlaps with the image. You can see the filter still overlaps, okay, when you're here. So it's possible to define the output, okay? I hope this clarifies how to handle the boundaries with the convolution. And let's move to convolutional neural networks. Any question, any comment? Aurelio, I already replied. Okay, perfect. Usually filters are 3 by 3 or are much bigger. So in convolutional neural networks, filters are small. Nowadays, filters are small. At the very beginning, they used to get filters that were larger, and we will see why we finally moved to filters that are smaller. However, say, in general, in signal processing, you have filters that are of arbitrary size and shape. I mean, the shape is typically squared. It's better to consider a shape that is squared, and in signal processing, at least, when you design the filter to be odd, such that you know you can clearly identify the center. Otherwise, if you take a filter that is 2 by 2, you don't know where the center is. I mean, you have to define where to place the center. While if it is odd, that they say 3 by 3, you don't have this problem. And then maybe you can design it, even if you want to use fewer pixels, then you can set to 0 when you are designing by yourself. Another question from Giuseppe. Why not use the same value as the nearest pixel? Sorry, what do you mean? For padding, yes. So what is, yeah, this is like closer to the mirroring. Say if you have 1 here, you want to have 1, 1, 1, 1. This is the padding we see for example, for data augmentation. Yes, this is something you can do. I'm telling you, I think the default option is to pad with 0. Is it possible to do a periodic padding on Keras? I think that you have to go to the options of the convolution or the correlation functions it's going to be scikit-learn, I think, where there is scikit image package. There you can find the same commands as you can find in MATLAB. And in MATLAB, it's I think you can find it in filter or in the correlation option. Yeah, I'm sure that there are plenty of options. Yeah, in others. Okay, here you are. This is your first convolutional neural network. I've just prepared today. Because the picture I was using before, I discovered had an error. And then you will figure out where the error is. Now, this is a network that is meant to classify images. This is the input, and these weird guys are the different layers of the network. What you see here is what you see when you draw a convolution, a feed-forward neural network. When you draw a feed-forward neural network, what you see is the value of what you draw are the values of the neurons, right? And here what you see are like the values of the neurons, are the activations. You don't see the weights. Weights are not being represented here. While in convolutional in the feed-forward neural networks, you draw them typically. Here you don't. You don't draw the weights. Now I tell you where the weights are. What you see here, what I want you to understand now, is that the image, first of all, preserve its spatial dimension. So you start from an image, and what you get, these neurons are still set over an image layout, right? So you preserve the spatial coherence of your image. Then what you get, what happens also, what can you see out of this network? What happens to these, you can see to these as the activations, which are the results of some processing, which I'm going to detail soon. So what happens to this activation? What happens to the image, please? Just let me know in the chat. They get smaller. Yeah. The spatial extent of the image gets reduced, and it gets reduced like abruptly at a certain point. So in particular here, it's kind of getting halved, right? So the spatial extent is getting reduced. And then further, it's getting reduced further because you see it is becoming much smaller, correct? Then another observation from Simone is that what happens is that the depth of my image increases. So my image at the very beginning, I don't know, is going to be, here I can say 128 times 128 times 3. And according to this notation, which you can find here, this means this should be written as 3 at. But this is a notation for the drawing, so don't take this as a default notation. So here the image has 3 color plane and say 128 times 128. Then it becomes, after the first layer of the network, it becomes some activation which is 8 by 128, so which is say an 8 channel images. Okay, and then it suddenly jumps down to a much smaller resolution, like each dimension is being halved. And then this operation is further processed, as you can see here, with different, again, by reducing the spatial extent. Here you reduce the spatial extent a bit, and here you increase the depth. And then further, you further reduce the depth again, until you get to 1 times 256, which has to be considered as a vector. Okay? And now I'm telling you which are the major ingredients, okay, of this network. So I will present all the layers that actually perform this operation. What I want you to give the intuition is that what happens to your image is that at the end of the day, at the end of the network rather than the day, your input image loses a lot of spatial resolution until it gets to a single vector here, right? And then it gains what it gains instead in depth. So you reduce the spatial resolution of this data, but you increase the number of channels of your image. Okay, so let's now analyze each and every layer that made this possible, and then we will go through all this picture and all some example of neural network. So the convolutional neural networks are made of 3 blocks, let's say. So there are 3 major blocks composing a convolutional neural network: the convolutional layers, the nonlinearities, and the max pooling. Now I will tell you, I'm explaining you exactly how it works. So that was just an illustration. So don't take this as an explanation of a convolutional neural network. This is just for you to get the flavor of what happens to an image. And what happens is that you preserve the spatial resolution, the spatial dimension of the image, and because the activations you see are still kind of images, but they reduce in spatial extent, in spatial resolution, and they instead increase in depth. And now you will see why, how this is possible. So there are 3 major blocks, and these are the convolution, the nonlinearities, and the max pooling. And what happens to an image is that an image has to be considered as a volume itself. Everything has to be considered as a volume, which has 3 dimensions: depth, let's say spatial extent, and x and y, say rows and columns, and depth. As you can see, height, width, and depth. And all your data and all your activations, so like the values in the neurons, are organized according to a volumetric, according over a volume. Okay? And what happens is that these volumes actually, here the volume was kind of unrolled, but you can see exactly the volume here. What happens is that the volume increases in depth and decreases in height and width. Now, the first layer to understand are the convolutional layers. And the convolutional layers are actually identified by a single convolutional layer is identified by a filter. So a set of weights, as those I was showing before with the convolution, and it operates as follows. This convolution takes as input, okay? So the convolution is performed over, say, a spatial extent, which in this case you can see is this block highlighted here. and these correspond to the weights you can find here. And the convolution, here it is not explicitly written in the formulas because otherwise it will be, so this index I, it's a general index, but it will span over the 3 channels of your image. So then there is the same mechanism. So it is like the correlation I was showing you before between the 2 color images, right? But this is the input image, and the filter is something like small, which in this case should be like, say, take the filter which is 3 by 3. But in order to compute the correlation, the convolution against a volume in the input, say an image which has 3 channels, the filter also needs to have 3 channels. Okay? So your filter can now be superimposed to each location on the image and define an output in the central pixel where it is located. So what is important is that the convolution mix all the input components along the depth. They are mixing them together by using different weights, because the filters have, in this case, are 3-dimensional as well. But the mixing is performed to all these values here. And so what you get when you compute the convolution, say you set padding option equal to, say the padding option to be valid, to be the same, and you're using a filter that is 3 by 3, you will get as output a single layer, right? Which contains a single value, which is where this neuron live in illustration. So for each location here, spatial location, say X and Y, you get in the convolution a single value which will produce, say, a slice of this volume. So this is going to be the output of the convolution against filter 1, say W1. W1ij. Told you it's a bit overly simplified because there is also a 3rd dimension, which I did not include it, but imagine this summation spans through all the 3 channels, right? So how can I get more, how can I increase the depth? So say here we are to the depth 5. How can I increase the depth of my volume? Please try to guess. Yeah, wait, I should add more filters, okay? And let me check the chat. But why are you so shy? You don't want to unmute yourself? So Daniele, now I think you understood why the convolution, how it is possible by convolution to increase the size of the depth of the volume, right? 1 slice per filter. You want a volume with more slice, you use more filters. Okay. The output layer is the first in the formula, exactly. So it's the first slice. And Simone, the filter that is 3 by 3, originally as before I was drawing them as 3 by 3, the filters now, in order to be used over this input volume, need to be 3 by 3 by 3. And in general, what up? Just a minor point. There is also a bias associated to each filter. Okay, so each filter has the coefficients of the filter, which are those lying over the like these 9 numbers. Plus, there is also a bias. So in this case, each filter has 10 coefficients, 10 parameters, okay? Francesco, how does the circle represent? The filter generates the first layer, right? The filter generates the first layer, you're right. And this circle represents like the output of the filter in a single position, like the central pixel of the convolution. So this circle in this illustration is the output of the convolution over this highlighted region. If you move to a different, like this circle, it's going to be the output over this other region. Correct? So in a single convolutional layer, we can apply multiple filters. No, Mahmoud, sorry. Yes, you're right. In order to increase, if I have a convolutional layer contains multiple filters. And the size of the output volume, the depth of the output volume, it's equal to the number of filters being employed. Why would I want to increase the volume? Well, this is like what happens in a convolutional neural network which proves to be successful. Maybe that will be more clear later on, but the idea is that each value here in this activation, after having gone through all the steps, these should contain information that refers to a rather large region in the input image and that comes from multiple layers before. So that should be a high-level information from the semantic point of view, say from the pattern point of view, and at a low resolution. So you want your network to, as you go deeper, to extract more kind of patterns rather than, and in order to do this, you need to increase the volume as you move further. Yeah, and Alessandro, it is going to be more clear as we introduce all the concepts and we see all the mechanisms. But this is just, all the neural networks are doing something like this. And they are called deep because you stack multiple, all convolutional neural networks are called deep because you stack multiple. So the filter steps involve 8 filters. In this case, yes, Francesco, in this illustration, the first layer is a convolutional layer which has 8 filters. The process, Xiaoyu, no, the process of convolution make the image smaller but deeper. No, the process of convolution doesn't make the image smaller, not yet. We are not done yet with the image that becomes smaller. It makes just the image, it makes just more activations. And the values you have in the activations are are mixtures of some values in the input volume around a specific region. Francesco, how can we choose the filters that make sense? We are not choosing anything. We are going to learn the filters. So we just need to define the parameters and to define how many filters and of what size. But I mean, this is part of the trick. There are some guidelines, like when you design a neural network, you don't know how many neurons to place in the hidden layers. There are maybe some practical rule, and here practical guidelines, and here the same. There will be practical guidelines on how to design the filters, how to define the filter size. But then the values will be learned by the image itself. So a second filter, W2, okay, I've messed up the indexes. The second filter, will provide you a different slice. And the third filter, another slice, and so on. Okay, I'm not calling them layers because the layers are the layers of the network. I'm calling them slice for the network, for the volume, sorry. So just to recap, the convolutional layer, each convolutional layer has multiple filters, and each filter mixes all the input components. The output is also a volume, and it's called activation maps. So that is equivalent as the neurons in a neural net. So each filter provides the output in a different slice, and each filter has the same depth as the input volume. And the filters have the parameters. So the parameters inside the filters, the weights of the filters are actually what you learn in your network, as we were saying. And the operations being performed, guys, don't forget, is always a linear combination. So it's like for a neuron, you have a linear combination of all the input for an hidden layer, you got a linear combination of all the input neurons in a feed-forward neural network. Here you will have, again, a linear combination. But the filters have typically a very small spatial extent. So you will mix only a few pixels in the input in a small region, in a small spatial region. Depth-wise, you take always the same, you hold the input, okay? And indeed, when you're implementing your first convolutional neural network, you are never specifying the filter depth, because the filter depth always corresponds to the number of layers of the input volume. But now, for example, if you want to attach here, so this is 32 by 32, right? If you want to attach here another convolutional layer, the filters will have depth equal to 5, okay? Because they need to mix all the components in the depth in the volume, okay? So let's see some convolutional arithmetic. No, so you are given a one input map, and I give you one kernel which is 3 by 3. What you get as the output. So this is like one input image, one simple kernel 3 by 3, computed convolution. What is the output? Guys? Come on. Is the question clear? Sorry, the kernel is a synonym of filter. So you are given the input, which is just one layer. So the one slice, the depth of this image is 1. So let's take it to be 32, doesn't matter. You have a kernel which is 3 by 3, padding options to be set to preserve the size, so padding with zeros. So the output is going to be an image which is 32 by 32. Correct? One slice, same size as the input. Perfect, Alessandro. Yes, this is a simple, this is a convolution, and this is a simple convolution which can be seen even as a convolutional layer. What if I give you 2 kernels, so 2 filters? What is going to be the output? 2 slices, same sizes. Perfect. So you got 2 outputs, one volume of 2 outputs, 2 slices. 3 input maps. And I want to take 2 kernels, 2 filters. Each filter now needs to have the depth equal to the depth of the input. Okay? So the output is going to be 2 slice. The moving guy, this guy here, is going to be given as the result of all the shaking filters and the convolution against the input. And similarly, the other shaking guy. Is it clear why it is 2 and not 6? No, not clear. Okay. Here you have... Okay, stop. 2 filters. Please, ask a question. Maybe it's gonna be simpler if you talk. We are given two filters, right? And now these two filters need to have, each filter needs to have the same depth as the input, right? So the input is, say, 32 by 32 by 3, and the filters need to be 3 by 3 by 3, where this is the spatial extent and this is the depth. Because this depth has to be equal to this depth. They have to be equivalent, right? Now, what happens is that when you compute the convolution, yeah, we have two filters, exactly. You have two filters, and each filter need to have 3 depths, 3 slices, because it has to be used to compute a convolution against an image which has depth, a volume which has depth 3. It won't be possible otherwise to compute the convolution, right? The picture, Marco, the picture looks like we have 3 filters of depth 2, you are right, but then we cannot compute the output against 3 filters of depth 2, because you cannot associate each, because the number of channels in the filters needs to be equal to the number of channels in the input. Okay, so now what happens is that the output is going to be 2, only made of 2 slices, and the shaking one is taking the result of the convolution of the filter that is moving against the whole image. So this is a volume. Okay, and the same to the others. Okay, no, it is not, Carlo. Carlo, please unmute and ask the question. Maybe it's going to be more clear for everybody. I'm sure that someone else didn't get it. Don't be shy.
Can you do again the example with 3 input maps and only 2 filters?
3 input maps and sorry, how many input maps? Sorry.
3 input maps and 2 filters.
Yeah, like this one. Okay. So it is clear that the depth of the input maps, the number of slices in the input volume, okay, need to be equal to the number of to the depth of each filter. Okay, so 2 filters that are, say, 3 by 3, and this is the spatial dimension, by what can be here, the number. So you have, okay, what can be the number here? I mean, it cannot be any number other than 3, correct? Otherwise, it won't be possible to compute the correlation, because you would have a slice here that has 3, like in the illustration from the previous perspective, right? You have a slice that has 3, you have a filter that is 2. You cannot compute, you cannot mix all the channels, right? It won't simply work. So it has to be 3, correct, Carlo? So far it's okay?
Yes, yes, now it's clear, because I thought there were 3 filters, but only 2 are.
No, it's 2 filters that are 3 by 3 by 3 necessarily. And the output volume is then, each slice corresponds to the output, to the convolution of each filter. Like, so this is the filter 1, 1, 1, and gives you the output 1, and this guy is the filter 2, and will give you, will be given by the convolution against the output, against the second filter. Now the image is clear. We have 2 filters of depth 3, yes. So the depth of the filter cannot change. when you design, when you implement your convolutional neural network in Python, you do not even have to specify what is the depth, because the depth it is equal to the depth of the input. So sorry, you don't have to specify the depth of the filter, of the filters, yes, because that is equal to the depth of the input. Okay, we have just had to specify the number and the size of the filter. At the end, the output, Marco, is a volume which has the same number of slices as the number of filters. So 3 images with 3 filters produce 3 images, right? Produce one. So if you take like 8 filters now, because there are too many 3, okay, you will get an output which is dimension 8. Okay? So what does, Francesco, what does the depth of an image represent? So no, this is not a stupid question. It has to be very clear to everybody, because otherwise this is going to be complicated. As I told you before, you have to think at the image as what is being processed to the convolutional neural network as a volume. So the image itself, so the input image, say this is the input image, can be seen as a volume which has the number, the spatial extent, say 128, a small image, 128, and then the depth is going to be the number of color channels. Correct? And if you are feeding a grayscale image, the number of color channels will be 1. So you got a volume which is only 1 slice. But then the concept of volume actually is preserved to the network even in the activations. So you don't have a clear meaning of the channels, like the color channels of the image, but each slice here, which can be considered as a channel in the activation layer, is just the result of the convolution against a filter. That's okay now. Perfect. Any other question?
Professor,
Please.
go ahead.
It's okay?
Okay. I have a question. Am I correct in assuming that the total number of output maps is the total number of kernel maps divided by the total number of input maps? So 6 divided by 3 gives 2 in this case.
No, what you mean by total? So the number of slices, say the number of maps, is equal to the number of filters.
Yes, but I have to associate every kernel layer with an input layer. So by grouping, in this case, 2 by 2, I get it's like a division. Did I explain myself?
No, yeah. Look, in this case, this moving filter goes with this goes with this, and this goes with this, and you provide 1 slice in the output, which is this guy.
Okay. Yes.
And so, I mean, you can have if I give you in the input 13 input maps, and I give you 2 filters.
Yes.
Which are 3 by 3 in spatial extent. The output, so each of these filters, what would be the size of each of these filters indeed? It's not 3 by 3, but it's going to be 3 by 3 by, Jacopo?
13.
Great. And how many outputs will you have at the end?
Well, if I have in input, how many input maps do I have?
13.
Oh, and I use a 3 by 3 by 13, so I will only have 1 output map.
No, you're having 2 filters.
Oh, so then with two filters, then I have 2 outputs.
2 output maps, you see? Because,
the total. Oh, sorry. The total number of kernel layers is 26.
That was your question. Okay. Yeah. Yes, but you never look at them like this.
No, of course. Yes, it was just a arithmetic trick, maybe.
Yeah. So, okay, then you can answer this. How many parameters in this case?
Wait,
Because
give me a second.
this makes sense. I mean, instead of computing the layers, compute the parameter, because you never look at the filters like separately. You always take them like as a whole, as a filter. Okay, you don't separate the slice of the filter. You take them always as a whole.
Okay, then it's 3 times 2 times 3 times 3. So that's
So 3 by 3, it's each square, right?
yes, and I
Then
have
we
6
have-
of them.
By 3, it's each. No, okay, this is each square. This is each filter. Okay.
Yes.
This is by 2. Yeah, it's exactly the same, but I prefer to count them as filters, right? So two
Okay,
filters.
that's okay. So it should be 54, right?
So it's 3 by 3 is 9, by 3, 27, 54. Is it correct? Plus 2 biases. Right? Because
Yes.
there are always biases. Don't forget about the biases.
All right. Thank
So
you.
Davide was okay. Thanks, Jacopo, for your questions. Okay, so there are overall 56 trainable parameters. Is it everything clear to you? Because this is something what we always ask some convolution neural network arithmetic. It's something we always ask at the exam. Okay. Any
Sorry.
question? Please.
Can you repeat how to count the weights?
So the number of weights here is now each filter is 3 by 3, right? So there are 9 parameters in each slice. But the filters contains how many slices? 3. So this is 27. How many filters you have? 2. So it becomes 54. But these are the weights associated to the filters. So which you use to compute the convolution. There are also biases, which of course we all forget about biases. You see, there is also. And each bias is being associated to each filter. So here, how many filters? 2. How many biases? 2. Correct?
Okay, so we have a number of biases equal to the number of filters.
Yes. Each filter has as I say, a spatial extent, which is something you define. In this case, was 3 by 3. Has a depth, which is automatically defined by the dimension of depth of the input layer, and then plus there is one bias, always. These slides are not there because it was hidden. There was a quiz. I will upload them. You also. Sorry, Prof. How do we combine the 3 input maps with one filter to obtain one output map? Simone, it's actually the convolution. So you take this. Look, I should go to this. Okay, guys, give me 1 minute break. Just 2 minutes break. I will find you an animation for this. I will grab an animation for you. Just 2 minutes. Say 2 minutes past 6. I'm back, and I will show you this to you, so you see the animation, because this seems not to be very clear still.
Professor,
Yes.
since we have 3 hours, maybe can we do 10 minutes break?
Yeah, I didn't want to take like 3 hours, but okay, if you want, okay, let's take 10 minutes break. 10 past 6, we are back, but I won't take you until 7:30. Don't worry, okay?
Okay, thank you very much.
Yeah, okay, sure. 10 minutes break then.
Professor, can I speak?
Yes, you can.
Yeah, Professor, can you just go back to the slide where you were explaining?
Wait. let me just grab the material for the convolution. Then maybe you ask at the end, okay? When we start the lecture, okay?
Okay.
Let me grab these first. Otherwise, I won't be ready there. Okay, thank you.
Okay, bro. Yeah.
Okay. I'm back. Sean, please.
Yeah, Professor, can I just open the slide once? Like it will be easier for me to then explain it to you.
Okay, which slide?
The one, yeah, this one. Yeah. So, Professor, just correct me if I'm wrong. What I understood is that now in the input maps, my depth is 3, right? So,
Yeah.
I am having my kernel 3 cross 3, where 3 cross 3 is the number of parameters. This is directly proportional to the number of depths in the input map, right?
Yes. Here, okay. So here there are plenty of 3, so it's not nice. But say the filter were 5 by 5. Okay. Just change it to 5, just for such
So,
that.
this is possible.
So this is 5 by 5, this filter, okay, instead of 3 by 3. So now you have 2 filters which are 5 by 5 over the spatial dimension, but over the depth they need to have 3 slices. So the dimension of the filters will be 3 by 3, sorry, 5 by 5 by 3.
So, so when you're telling it's 5 by 5 by 3, it's 3 because the depth in my input maps is 3, right?
Exactly.
Okay. Now, Professor, now tell me one thing. This when you're telling this 5 by 5, is it like, how are you deciding it? How are you choosing it will be 5 by 5 or 3 by 3 or something else?
This is part of the design of the network. This is like when how many neurons should you put in the third hidden layer?
Okay, so that's completely based on like the number of epochs or the number of things that we are trying to run in the entire thing, right?
This is part of the design of the network here.
Okay, okay. And two is the number of filters. This is
Yes.
also the part of network, right?
This
So in the diagram you wrote 3 into 2 into 5 into 5 right now. So 2 is the number of filters that we are having of depth 3 and 5 into 5 parameters.
yes.
So how are we deciding the number of filters over here?
How many neurons would you put in the 7th hidden layer of your feed-forward neural net?
Okay, okay. So that's again completely on us. Like it can be 2, 3, or 4, the way we want, right?
Yes. Yeah, this is part of, I mean, there are some guidelines which we will see. There are some successful architectures which I will illustrate you, but then I mean, there is no formula giving you the best,
Okay.
the right number to use. Okay.
Okay,
So,
Professor. Thanks.
you're welcome. If there are still some doubts on the, no, not this one. So this is a site I'm continuously citing in my slides, at least in this first part. So this is, now I cannot draw, but I can point with the mouse. So this is the input volume, 3 layers. Say it's 7 by 7 by 3. So the spatial extent is 7 of the input volume, the depth is 3. There is a padding, the zeros around. There are 3 filters involved. You can see them here. W0, no, sorry. There are 2 filters involved, W0 and W1. What you see here through this animation is actually what is being computed. So the pixels and the filters coefficients involved in order to get to each output you can see here. So when you're computing when you're using the first filter, you get output over the first slice. I should record it. Okay, let me conclude this. When you are using the second filter, you're getting output over the second slice. Okay? And you see what is being involved is highlighted. You always involve some the region inside the image, right? The filter and the biases. Now the filter is kind of jumping here. We see it's not moving. It's not moving of a single pixel. It's moving of 2. And this is called. I mean, I didn't want to enter in this detail because this is called the stride. So how far you jump with your filter. Typically is 1. I mean, let's take this as 1 for the very beginning. So let me go back and start the recording now. Is it okay? Is there any question? Okay. Perfect. And you also managed to get the yeah, the link is, I mean, it's acknowledged always when I'm using in the slides. So I will fix also these numbers that are kind of misleading, and maybe I will write it 5 such that it's easier for you to understand. Okay, let's move further. Now, which are the other layers? There are activation and pooling layers. So activation layers is like activations in the feed-forward neural network. You have to include some nonlinearity at a certain point. Otherwise, everything will collapse to a single linear combination of the inputs, right? So there is no point of stacking multiple layers in a feed-forward neural network if you don't include a nonlinearity. So here, you have to include a nonlinearity exactly after each convolutional layer. And the nonlinearity that is mostly used in a convolutional neural network is called ReLU, rectifier linear units, which is thresholding. Say, this is the input, this is the output. If the value in the input is between 0 and 1, say, okay, larger than 0, so here is the range is between 0 and 1, but whatever is the value, whatever the value is, as far as it is positive, it returns the values untouched. But if it is negative, it returns 0. So it is exactly this definition. Okay, that was used to be more effective than the sigmoid, and you can also find the leaky ReLU, which is just shrinking very heavily towards 0, the negative values. That was used to say avoid or say somehow mitigate the dying neuron problems, which you start having when the neural networks are becoming very deep. You can also find tanh and sigmoid as in traditional feed-forward neural networks, and indeed the first convolutional neural networks were using these activation functions. But now most of them are based on ReLU and leaky ReLU. You can see the differences in the activation functions here. Okay. Is there a question? I cannot grab the chat. Question? Please ask if it is something relevant. So Fabio, yes. After each convolutional layer, there has to be a nonlinearity, an activation layer. Indeed, in Python, there is not even an activation layer. You just have to specify the kind of activation function to be used in the convolution layer. Okay? The type of activation function to be used. And then there are the pooling layers. So the pooling layers are meant to reduce, please, is there a question? No? The pooling layers are meant to reduce the spatial size of the volume. Okay? So the pooling operates independently on every... It does seem to be... Daniele, do you have a question? No, just mute. Okay. The pooling layer operates separately on each slice and operates the same. Okay. So while the convolutional layer is mixing all the layers, the pooling layer operates layer-wise, slice-wise. The convolution is mixing all the slices. The pooling layers are just operating slice-wise, and they just reduce the spatial extent. So the most widely used is called max pooling, and this layer just takes the maximum value out of a predefined range of values. So in this case, this is a max pooling 2 by 2 because it takes the maximum over a region which is 2 by 2 in your input slice, and you see over the red region you got the 6, over the green you got the 8, the blue the 4, and elsewhere the 3, because this is the max. So if you take a max pooling which is 2 by 2, you reduce the number of activations of the 75%. Okay? And then at the end, there are dense layers. So guys, I just realized that when I prepared this figure, these numbers are, I mean, they can be these numbers, but are like counterintuitive, right? So that should be, I will fix that 64 by 64. And you can see here that should be, it's not 16, but 32 by 32. Okay? Yeah, because unfortunately these numbers, there is this tool for generating this network. I was so happy to use it, and I didn't check that the numbers were not consistent as I would like to. So at the end, okay, but as you can see here, what happens is that you got at the beginning 8 filters. You don't know, if you take the size of the input image, you take to be like 128, you take 0 padding, not to have too many troubles, but I mean, then we will see what happens when there is padding. The max pooling is downsampling of 2 each dimension. You see you go from 128 to 64. Then there is another convolutional layer here. How many filters in this convolutional layer? $24. Because there are 24 outputs, what is the size of each filter? We know we can assume it's 3 by 3 by 8. Correct? So this convolutional layer will have 24 filters. Is it clear to everybody? Otherwise, please unmute and ask. And then here there is a...
Sorry, Prof. The last layer of this convolutional network is like 256 at 1.
Wait. Now we get to this. Probably you have to arrange this as well. You have to fix this as well. Okay.
Okay.
Give me a second. So, but because this number were kind of set, I thought that there was like kind of consistent architecture. Indeed, they are not. I will fix them in the slides. So I will upload. So, but then I'll tell you why I did this change. You will tell me because there is another quiz. So here, then you get to the max pooling. By the way, there are no parameters in the max pooling, right? So you downsample by 2. So you got a volume which is 32 by 32 by 24. The depth is 24. And then here, there is some reduction in dimensionality. In principle, this you should get to a vector. Or you stack other layers, other convolution, let's say, plus max pooling. And of course, activations are here. Okay, there is convolutions plus activations is always there, right? Until you get to this number. And this can be done by max pooling and by using a different number of convolutions. And then at the end, what happens is that you have what is called a dense layer. A dense layer is nothing but a multi-layer perceptron network. And it's also called the fully connected layer. So there are some notation that are like dense, it's in Python. Fully connected layer is in more when you describe the network, the architecture. And but anyway, this is just a multi-layer perceptron. So here this is dense in a sense that each output neuron. So in this case, if this were a network for classification, the classification probably should be over 128 classes, right? And here, each neuron is connected with his own weights to the input. And so you see how it is performed, right? This processing of the network, how the network, how the image progresses to the network into these volumes that contains activations that can increase in number by the convolution, can decrease in size to the subsampling layers like the max pooling, even though it is possible also to decrease a bit the size by the convolution because you can exclude the pixels at the border, or you can do some downsampling. So don't get crazy out of this number. I will fix these numbers on top of these. I thought they were consistent, and but is it still hidden? Sorry, maybe I have still an hidden slide. No, okay, it's right next. So let's see what happens with your convolutional neural network in output. Okay, so you feed an image to your network, and this is the input image. It is being fed to typically a bunch of convolution. Okay, the ReLU, which is the activation, which goes together with the convolution. Here, it is separated just to visualize what actually the convolution, what actually the ReLU does. And then there is then there are like you can plug in a bunch of convolutions. Then there you place a pooling layer, right? And then again a bunch of convolution layers, and then a pooling layer until you get to a vector. And now, so at the very beginning, your input is an image. And now let's assume that instead of showing the volume, I'm just taking each slice and bringing this slice back to here, right? And now what you get is that the first convolutional layer, so each of these will be associated to a filter, which is, I don't know, whatever size, 5 by 5 or 3 by 3 by 3, because the image has 3 channels, right? And what you see here is that, so these images are just the slices of the activations. You see that there are still some shapes related to the car, so you can see the car here, right? And this is because this is the output of the convolution of the image against a filter that is, I don't know, 5 by 5 by 3. So you preserve the shapes because you are kind of mixing together pixels over a 5 by 5 neighborhoods and over the 3 different colors. You won't get something much different from something of this type, of this kind, right? This is the output of the convolution. Then what you get is the ReLU. What the ReLU does is to set to 0 the negative pixels and keep only the positive ones, right? And the positive ones are left untouched. So while these to be computed takes all the 3 layers as input, this takes only the output of the ReLU is given by just the input of the very same slice, because the ReLU operates layer-wise. Then here is another convolutional layer. This convolutional layer means that in order to get this, you take all this depth, all this volume, all these 10 slices, whatever, and you mix them by using a filter that here has to be, I don't know, 3 by 3, say 3 by 3, by how many slices? 1, 2, 3, 4, sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, by 10. So each of these guy is taking as input them all. And you see that maybe some shape pops up again because it can be somewhere else in the previous output. It can have been preserved by some other convolution and by some other rate. And then again thresholding until you get to here where there is the max pooling, the pooling. And you see that the spatial resolution decreases. Actually, we should have drawn this slice is smaller, say half a size. But for the sake of visualization, you take, in this illustration, just the pixels have been increased. And then you continue stacking these blocks, which are like convolution, ReLU, pooling, convolution, ReLU, pooling. And at the end, after the last pooling, you get to a very small image, right? And this image is, in this case, sorry, it's a depth which is 4 by 4, right? Its slice is 4 by 4. It's a volume which is slice is 4 by 4 by 10. So it's not many values here. It's 160. Here there are 160 values. You can place these 160 values and throw them directly into a feed-forward neural network. This feed-forward neural network then a multi-layer perceptron, a fully connected, a dense layer, call them whatever you want, will perform the classification of this image into the categories of the Cipher-10, for example, dataset. Okay? So far, so good. So this vector 116. It's exactly what you get here as the output of the convolution. And in Python, typically, you need to specify that you want to do this operation, that you move out of the volume into a vector by what is called the flattening operation. But these are a minor technicalities. And it's called the flattening layer, but it's just unrolling this volume into a vector and then feeding it to a convolutional neuron. To a multi-layer perceptron. Is everything clear? Yeah, I assume yes. No questions, right? No comments? So you tell me.
Excuse me, Professor.
Please.
I was wondering, is there, I mean, I'm sure there is, but like, what is the reason why we keep doing more filters and lowering the resolution? Like, what is the idea behind it?
Because the value here, now, after all this processing, it's a value that refers to a rather large region in the input, and it contains the result of multiple operations that are linear combination and nonlinearity, linear combination, nonlinearity, linear combination, nonlinearity. And this will become a feature. So probably this value will be large, whether there was a kind of white region in this part of the image, or whether there was like a pattern like that resemble an eye of a human being or whatever. And then you can train everything, which I mean the filters coefficient and the weights of your dense fully connected network in an end-to-end manner. You feed images and you want your network to, we will discuss this maybe next lecture, you want your network to learn which parameters minimizes the classification error. And you are learning both these filters and the classification weights at the end. Okay? So that was the figure I was using before. But then I discovered there was an error while doing the lecture. So I changed it, and then I realized also there was an error. I mean, also the numbers in that need to be changed, and I will update them. Can you tell me, can you spot the error? This is from Wikipedia. Subsampling increasing depth, exactly, Luca. The subsampling cannot increase depth because the subsampling operates layer-wise. So this shouldn't be there. Okay? And then, of course, also here, the depth is increasing. It cannot be. Good. So, okay, let me just briefly briefly present the first convolutional neural network. And for this one, where we see the architecture, like carefully, with all the parameters, then we conclude. So that was proposed in 98, 97. I think it was 97, maybe the publication, isn't it? Proceeding of IEEE, it was 98, sorry. So that was meant to classify images of 32 by 32 pixel grayscale into 10 digits. And so here also this illustration is not correct because there should be a number, because they were classifying digits. So let's say place the number 9, 100 digits. And I can tell you that why is it meant for classifying digits and not letters? What does suggest you that is meant for classifying digits while not letters? 10 outputs, exactly, Luca and Lorenzo. So, I mean, except from assuming that the network was classifying only 10 letters, but most probably it was classifying 10 digits. So it takes as input an image that is 32 by 32. And then, how many filters are here? 6. Because you see that there are 6 layers in the output, right? And these convolutions are 5 by 5. So there are 6 filters that are 5 by 5 by the depth. The depth is 1 because the image was grayscale. Why the filters were 5 by 5? How can I say that the filters were 5 by 5? I can see these from the fact that the input size reduces by 4. This is because they were performing the convolution using the valid option. So indeed, this was also decreasing the size. Then there was a subsampling, which was done by average pooling, not max pooling. Max pooling, then in practice, is find out it is preferred because it introduces an additional nonlinearity. Okay? So the downsampling here brings your image from 28 times 28 to 14 by 14, so your volume. And now here you have other filters. So how many filters? The number of filters here you have here is 16. Because you have 16 output slices, right? Your volume has 16 output slices. And the size of this filter is again 5 by 5, and indeed you lose 4 rows and 4 columns. Okay? Is this very clear to everybody? Then there was a subsampling again, which was decreasing the spatial extent by half. So you get to a volume which is 16 in depth and 5 by 5 in spatial extension. And then this was directly fed to a fully connected layer having 120 neurons, and then a hidden layer, 84 neurons, and then a hidden layer having 10 neurons. So here is the architecture of the network. And this is, if you assemble this architecture in Python, and then you end in, I mean, there are some slides next. Maybe I will show them very quickly because Francesco will go through them, through these concepts more carefully during the exercise session, the lab session. The first, when you prepare a model, then you can see the model summary. But this is also for the feed-forward network, so I think you're familiar with this output, right? So the first, the layer, each layer has a name and then a size. And now you can see the size. Here, the first is none because it is meant for the size of the batch. So how many images you feed for training, say along the 4th dimension, which is the dimension of the batch for computing gradient. And you get this, the shape of the output, which is 28 times 28 times 6, which is exactly what you see here. And then you have the number of parameters. The number of parameters, so we told there are 6 filters. So today is boring because all these arithmetic, but it's really necessary for you to understand. This really makes the difference. It's not surprising, guys, that if you take this picture on Wikipedia, it is wrong. I mean, so many people talk about convolutional neural network, but I mean, they don't know the arithmetic, the basic arithmetic. You are like assumed to become an engineer, right? So at least you need to know this, at least these technical aspects, like safely. So there are six filters that are of size 5 by 5, right? By 1, because the depth of the input was 32 by 32 by 1. So here is the output is 30 times 6, 150, plus 6 bias. Here the same, you have how many filters? 16 filters of size 5 by 5 plus 16 biases. Okay? It's written better here, you see? 16 by 5 by 5. Ah, sorry. By 5 by 5, the spatial extent, by 6. And this 6 is because the input is 6. The average pooling layer has no parameters, by the way. Of course, it's just computing an average. So 16 filters, 5 by 5 by 6, because input volume is 6 slices, plus 16 biases. And you move, and then I mean, the convolutional layers are over. And then you get into there is this flattening. This is what I tell you, which performs this operation of unrolling this volume into a vector. And these are the output of the flattening is 400, which is exactly this guy. So 16 times 25 should give you 400. And now there is a dense layer here. So the how many parameters in the dense layer? 400 times 120 plus 120. Right? Each output neuron is connected to each and every input neuron. Each of these guys is connected to them all, plus 1 bias. So you can see this makes the number like, so 400 times 1200, not 12, 120 gives you a huge number. It's 48,000 plus 120. So all the parameters are here in this huge hidden layer, multi-layer perceptor. So this network was was still convolution, but the convolutions were just reducing a bit the size of the input, and then there was a huge fully connected layer that was taking all the parameters. And then you see here, okay, of course, it's 120 times 84 plus 84, and you get this number, and so on. So most of the parameters were in the traditional multi-layer perceptron portion of the network. And by this I'm concluding, what happens if you were just taking this image and you were feeding it to the second last layer to a fully connected network? Well, so this stands for a fully connected network, right? All these parameters are a dense connection. Each neuron here is connected to each and every of the other. So it's going to be 84 times 32 by 32, which is the number of input neurons. So like as I was showing you yesterday. So this is a huge number, say plus 84 plus this other guy, which is the cost of this. But of course, what is most expensive is this guy that you get around 80K parameters. Now, still, you can see there is not much difference in the number of parameters, because overall, with a convolutional network here, we got about 61K. If we were just feeding the network to a dense, like the second last hidden layer, we were getting to 86 parameters. But now, consider I give you color images. If I give you a 32 by 32 by 3 input, the number of parameters of the multi-layer perceptor will be multiplied by 3, because you have to roll the image, so it's going to be 32 by 32 by 3 by the dimension of the output, right? Instead, if I just feed you an image which is by 3, what does change is only the first filters, say the convolutional, the filters of the first convolutional layer. So in practice, instead of having the very beginning, you have like 6 filters that were 5 by 5, you should have 6 filters that are 5 by 5 by 3 in case of colors. This is in case of grayscale. So the number of parameters in your case is increases only of 300 samples, 300 parameters more. In this case, it gets to 3 times. So you can see how much I mean, you would have been very easy to use this network to move. So if you are able to train this network with such a large number of parameters, then that's not a problem to train a network which is meant for color images. But if you take a feed-forward neural network, then it's pointless. The number of parameters goes 3 times. And this is even worse if you take, instead of an input, which is 32 by 32, an even larger input. So what does change is not this part, because it's a convolution, the number of the filter size remains the same. I mean, you might retrain them, but the number of parameters doesn't change. You just have something larger here. Instead, if you just increase, this will be clear later, maybe with some example, if you increase the spatial extent of the image, of the input, and of course you have to retrain the network every time, okay guys? But if you increase the spatial extent, the number of parameters increases as the number of pixels, okay? So to conclude, really I forgot about this, but I think it's the right conclusion for today. This is another standard illustration of a convolutional neural network, where the image, this is the image, is being processed through the convolutional layers, which are convolution, pooling, and of course, plus activations, pooling, and then you are assembling a volume until you get to a very small volume in size. In principle, the volume can get to really a 1 pixel width, okay? And then this volume is rearranged as a vector. And then here there are fully connected layers, dense layers, or it's a multi-layer perceptor, we know, which performs the classification. So now getting back to the initial intuition, this part can be considered as the feature extraction. You remember, we have the feature extraction block, takes an image, the feature extraction block gives me a vector, and then there is the classifier, which gives me the output. And this is exactly what happens here. So this feature extraction block is this block. What you get here, it's what is called the latent representation of the image. So a vector that the network extracts from the input image. And this vector is meaningful for performing classification. Indeed, if you repeat the T-SNE experiment by now bringing nearby images that were nearby, not in their, say, ambient space, in the pixel space, But here, in the latent representation, in their latent representations, what you get is something like this. Oh, so this is not a cipher 10. This is cipher 100. 100 classes of small, tiny images over different categories. But you see that nearby you have red cars, you have landscape, you have yellow cars, you have coffee machines, which means that these objects, these images are from this, have a latent representation that are very close. And that's why and basically a classifier, any classifier over the latent representation would be good at classifying input images. Okay, thank you very much. I'm done. If there are any questions, I can take them. Very happy to take them. Please unmute yourself and ask. There is a question on the chat. Oof, how many questions? I lost plenty of them. No, this is okay. I hope I answered to the question from. No, the question from Khaled is new, fresh new. I will upload the slides by tomorrow. Yeah, hopefully. No, come on. Too long a question. Can you unmute yourself and ask them directly?
Professor?
Yes, please ask.
So you taught us that when we have some parameter tuning to do, we should apply cross-validation and such methods to try and get the best result and select the best value for that parameter. But how do we know that parameters are independent, that the best value, the best combination is just some not optimal combination of parameters that combined together give the best score?
So, sorry, what you mean? Say for the network design?
Yeah.
So for the network design, what you typically do is, okay, you frame to kind of reference architecture, standard architecture that is performing well, and then maybe you do some variation. And of course, here you can apply the best practices of performing cross-validation and assess the performance over an independent test set to finally choose the best architecture. In practice, in deep learning, this is never done because training these networks takes quite a lot. And typically, you are given a training set, you can use them all for training and validation, and then you are given an external test set in order to do this. And yeah, so you're not going. I've rarely met, say, works doing cross-validation like on these huge data sets. But in principle, this is possible as you do for whatever, for any other architecture. And so it's not, it shouldn't be different from what you do from when you want to try different architectures, say from a multi-layer perceptron network.
So you just take an existing one and try to modify it a little. Yes,
next lecture we will see what we can take out of a pre-trained network, an existing network, because I mean this network, there are very powerful networks around which we can take. But in principle, you take as a guideline these, like I think that even the first architectures winning the first competitions, like for a couple of years, were based on the LINET structure. Of course, they were huge. We will see them, AlexNet and VGG, they were huge, but they were the same principle. Convolution, ReLU, max pooling, convolution, ReLU, and then get to a fully connected layer with a very huge latent representation.
Okay, thank you.
You're welcome. Any other questions of Francesco? Julia will try to upload the slides, but you have to change the figure, so it might take a while. Khaled has a question.
How does backpropagation work for these kinds of networks?
The propagation you mean for training, then for the backpropagation for training the...
Yes, exactly.
Yeah, look, convolution are linear combinations. So it's exactly like a multi-layer perceptron. The only point is that the weights are shared. And we will see this in the next lecture. The only point is that you have to take care of the max pooling, but the others are like, so the derivative of the ReLU is 0 if it is, so you can't compute the derivative of this function. And so the only point is the max pooling, which we will get to that next lecture. It is very nice to compute the gradient, not only for training, but because you can also see, it's also a way to visualize what the network is learning. So you have to compute these gradients because you need to train the network, but then also as a byproduct, once you have all the gradients, you can use them also to maximize some activation and see some kind of visualization of what the network is kind of learning. Okay, any other question?
Yes, Professor, I have a question.
Please.
We did all the layers of convolution and nonlinearity and pooling to extract features, right?
Mm-hmm.
And I think I understood how this works, but I didn't quite get why applying all these layers extracts the feature. I don't know if I made myself clear.
Yeah, I mean,
I mean, we saw how the process works, but I don't know if I didn't understand or we didn't see why applying these layers extracts the features.
Well, do you see these from a multi-layer perceptron? You have some output. So here, when you are here, which is like one of the deep layers of your network, or like one of the deep layers in your, even in a fully connected network, so in a multi-layer perceptron, what you get is some kind of linear combination of the inputs, right? Sorry,
Yes.
non-linear combination.
Non-linear, no, yes.
Linear, it would be trivial. And so it is a feature as it becomes a feature when you are using a multi-layer perceptron. So if you translate the multi-layer perceptron by taking the nonlinear combination of the inputs can provide you a feature, then here you have the same. On top of that, sorry.
No, I was okay.
But then on top of that, we will see next lecture, there is also the receptive field, because there is this structure. So you don't have structure in a multi-layer perceptron because it's all the layers. I'm drawing them like the same, but each the same size, but they don't have necessarily to have the same size. But each neuron takes as input all the previous ones. In contrast, this pixel here, probably was say in the top left corner of this, which was in the top left corner of this, in top left corner of this, which refer to this region. And now you are kind of preserving the location in your feature vector. You are kind of preserving a location where the features have been extracted. And the deeper you go, you will receive for this the receptive field, but you can easily understand this by thinking at the convolution and the max pooling, what they do. You are actually, the deeper you go, the broader is this, which is called the receptive field. So the number of pixels involved in order to compute this. Then you are mixing together indeed colors of the image. So it has to be very challenging to extract the features, but how can you can extract from a vector when classifying it to a multi-layer perceptron or a nonlinear combination of the inputs? Well, then here should work the same.
Okay, thank you very much.
You're welcome. Other questions?
Sorry, Professor.
Yeah.
How did you compute the number of parameters for the dense layer 1?
Yeah. Then the dense layers are here. Yeah. So maybe I'm wrong. No, I'm right. So the dense layer has 400 No, I'm right because it should be Python, the computation. So 400 euros in the input, 120 in the output, right? Each output neuron is connected with all the inputs. And so it's 120, so it's 400 times 120, plus the biases.
Okay.
It's okay, Mark?
Okay. Yes. Okay.
You're welcome. You're welcome. Other question? What about images with different sizes? We will talk about this, but when you are here, everything breaks up. You can see that when you are here, everything breaks up. Not the flattening, but when you are getting to the dense layer, everything breaks. And then we will cope with that. We will live with that. Don't worry.
Excuse me.
Please.
So if it's easy to pass from gray images to 3D images, it's also easy to pass from images to video because I just have to change the first layer.
Yes, definitely. You see, if you take a multispectral image, it's not an issue by the number of parts. But you see, you have an architecture that is meant for that, and we will see next Tuesday. I'll be there, I think, and I will not Wednesday. Sorry, next Wednesday, and I will give you. I will show you what are the advantages of these architectures in terms of weight sharing and sparsity of the weights. I mean, it's nothing but discussion over this architecture, right? So next lecture we will see some discussion over this, and of course the first comment: if you take an image which is a hyperspectral image which has 100 channels, what actually changes is just this number of parameters. In any case, you might need more layers to cope with such a large amount of information. Okay, maybe I'm not telling you. So in principle, it can be fed to the network, but maybe since your input is maybe 6 filters at the very beginning are not enough for handling such a large dimensional input. Because if you think, if you take like 100-dimensional input, so you can see that the depth is always increasing here, right? As a kind of practice, as a kind of like best practice. If you start from 100-dimensional input, you probably have to take more filters at the beginning and not condense them to only 6 features. Okay.
Okay, thank you.
You're welcome.
Professor, do you hear me?
Yes, please.
Have two short questions. The first is, aren't we losing information in the last layers, because we could have like 2 images that after filtering have the same vector, the same final vector?
Yes, in principle, yes. Then what you hope is that the images belongs to the same class.
Yes, otherwise we have the wrong model.
Well, you don't have the wrong model. This is part. You have a classification error. I mean, there is a dimensionality reduction, okay, which is necessary because the information, as we mentioned in the images last time, it's very redundant. Okay. And of course, in this feature extraction, you might lose something. These networks are like they do some errors. They are not perfect, but that is definitely the case where. This is what you have to pay because of the dimensionality reduction. 2 images of different classes may get nearby. What you hope that features are such that they keep them far away.
Okay. So, and my second question is, in the first layers we are looking for general features, while in the last we are looking for detailed feature, right? Is it like that?
No, think of one value here. A value here is defined by taking a small region in the input. So you might look at some very small pattern discriminative pattern. Maybe it's, say you take a filter that is 3 by 3. You're looking at a region which is 3 by 3. But as you move deeper, this pixel refers to a larger region. So maybe you can find some high-level pattern that might be meaningful for recognizing the content of the image.
Okay, so it is reversed.
Yeah,
as I
exactly.
said. Okay, perfect. Thank you.
You're welcome. It's okay. Any other question? Still on the chat. Why do we use pooling layers? If I get it right, we can decrease the image size just by using convolutional layers. Yes, we can reduce the size by using downsampling, say by using the stride, so by not taking the convolution at each output. The max pooling introduces an additional nonlinearity. In some cases, yes, you can find networks that are without max pooling and just using the stride. We will see next the steps from feature extracted and training linear used for image classification. Well, I'm not spending many words on how to train these networks because you already seen how to train a multilayer perceptor, and I will tell you that this can be really expressed as a multilayer perceptor indeed. So the only point to see is to keep track of the max pooling, and that's it. Okay, but then then once you're very familiar with this architecture, when you know it, you will see that then you can apply all these procedures like stochastic gradient descent, Adam optimizer for training this network instead of the multilayer perceptor. Okay, so thank you very much and see you next Wednesday. Thank you. Bye-bye.